x value equally without regard to the fact that there is way more mass apparently at one position than at the other. So, for instance, let's say there were 3 kilograms over here, but only 2 kilograms over here. It would be silly to count both of those positions equally, because the fact that there's 3 kilograms at one means that's going to matter more. So here's my suggestion. To find x as the center of mass, I'm going to put in the x value more if there is more mass there, because that position is more important. So I might say take x1 plus x1 plus x1. I do that one 3 times because there's 3 kilograms there, whereas, I guess let me mark it like this. So that I did 3 times, and the other one I'll just do twice, 2 times, because there's only 2 kilograms there. So x1 is more important than x2. And then, of course, how many values do I have here? I have 5 values, right? So if I'm taking an average, I need to divide by the number of things that I have, right? So that basically weights the positions differently depending on how much mass is there, right? Well, in general, what am I doing? In general, what I'm doing is I'm taking x1 and I'm weighting it by how much mass is there. I'm weighting it by m1, and I'm taking x2 and I'm weighting it by m2, and then of course the sum is m1 plus m2. So that makes sure you divide by the right thing. This is our equation for finding the position of the center of mass. So it basically counts an x value more if there is more mass there. Which, by the way, I left this here on purpose because remember, the center of mass is going to be skewed towards the larger mass end. That's how we're going to make sure that that happens, by counting a position more if there is more mass there. It's not so different if you're trying to figure out you're standing in a class, right? If you have your various scores, maybe you got an A on a midterm, A on a quiz, and a C on the exam or something, right? You can't weigh a quiz and exam equally because they're not worth the same. So you go to the syllabus and you multiply each score by how much it's worth, right? So that's what you're doing here. Instead of test scores, they're positions. And instead of weights on the syllabus, they're literally masses. You count a position more if there's more mass there. This will work for however many things you want to include. If you're trying to do this for your entire score, then of course the sum of all the weights would be 100%. But you can also do it for some partial thing of your score, right? So let's say 45% of your grade is accounted for so far, you divide by 45 instead, right? So hopefully this is a familiar procedure, okay? That's how you find the center of mass. You just count a position more if there's more mass there. You weight the positions by the mass that is located at each one, okay? So let's go ahead and just try an example of this. And I think this is relatively straightforward, so I'll try to put in a few twists and turns. So here's my example. I have a point particle, mass 1. I have another point particle, mass 2. And I've tried to draw M1 a little bit bigger because it has more mass. And just to make things interesting, I'm going to say that the connecting rod itself is not massless. The connecting rod itself is going to be 10 kilograms. And my question is going to be is that if I wanted this thing to be able to, with a single support, stay balanced, where would I need to put that string? So where to attach a string so it stays balanced? So first of all, where is the string going to have to go? It's going to have to go at the center of mass, right? And looking at that, we can already see that there is definitely going to be more mass on the left end than on the right, so the center of mass is going to be somewhere over here. And I'm going to have to attach the string there. By the way, you can do this progressively and build yourself a nice little sculpture. This is called a mobile. Sometimes you do them in elementary school. So basically you have one master string and then you have a bunch of other things, right? So the physics behind that, of course, usually in elementary school you do it by trial and error. The way you do it, the physics of it is that every string is attached to the center of mass of whatever hangs off of it, right? So if you look at any given string, this one, the center of mass of everything below it is here. And that string directly supports it. That's the physics behind it. So that's what we're basically trying to do. Maybe this is the bottom piece of a mobile, and we're trying to hang the first string to hold it up. So maybe it's like this piece right here, okay? So first things first, I know the center of mass, generally speaking, is toward the left end, but I do have to account for the mass of the rod itself, and that's an extended shape. But luckily the rod, if we just ignore the two masses on the end, if we just think of the rod itself, we can take that as relatively uniform. So the rod is really a third mass. It kind of looks like this. So we really kind of have a mass 1, mass 2, and mass 3 system. Oh, I forget to tell you how long the rod is. So the rod, let's say that that is 5 meters long. This is a huge mobile. This is like a very large art installation or something. Okay? And then we take the mass of the rod itself as being halfway, okay, because the rod itself is uniform. So now we have to pick an origin that we're going to work with. Now I picked it over here for the purposes of kind of showing you arbitrarily, but there's no reason to pick it out here where there's nothing. Very typically, we just go ahead and pick x equals 0 at one of the masses or something like that. Because why not? It's just easier that way. You can pick x equals 0 wherever you think is most convenient. So let's identify x1, x2, and x3 that would go into the equation. What's x1? What is the position of mass 1 along this number line? 0. How about mass 2? This one. 5 meters plus 5 meters, right? How about the third mass, the mass of the rod? Plus 2.5. So I'm sure you can plug and chug those along with the given masses. And the output that will be given for XCOM will be plus 1.7 meters. And notice that it is coming in kind of exactly where we expect, plus 1.7 meters. It is skewed significantly toward the left, although perhaps not as far left as you might expect, because remember, even though there's 15 kilograms on the left end and only 5 on the right, we do have a big mass in the middle, okay? if you did the calculation omitting the rod's mass, you of course would find that the center of mass was even further to the left. The mass that's in the middle of the rod helps to swing it a little bit back the other way. Now, let's say that you got that answer, and you compare notes with a friend who's been doing the homework as well, and they say, no, you're wrong. The answer is minus 0.8 meters. And you get into a big fight over it, lose your friendship. And then 20 years later, you realize that you're talking about the same place. Okay? And the reason why is that your friend decided to use the geometric center as their reference. Nothing wrong with that. They would have different opinions about the values of all of these, x1, x2, and x3. So what would their x1 value be?
Negative 2.5.
Negative 2.5. What would their x2 be? 2.5, and their x3 would be 0. And if you calculated with those positions, you would get minus 0.8, which is exactly the same place. Okay? Relative to their number line, the position of the center of mass is 0.8 to the left. So for that reason, I want you to remember origins are arbitrary, and maybe you should express them in a way that doesn't assume someone knows what you like x equals 0 to be. So maybe here we'll say xcom is 1.7 meters to the right of the left end. And over here, you might translate that into more universal language like xcom is 0.8 meters to the left of the geometric center. And if you had compared notes like that, you could have saved yourselves that big fight and realized you're talking about the same place. Now, the reason I'm bringing this up is because WebAssign can't read your mind as to what you would like x equals 0 to be. So usually what it has on next to the box is where it's measured from. So it might read, so WebAssign might ask you to fill in this box, of course, the number. But then it already provides the language there where it's referenced from. Now, if you didn't look ahead and see that, which is totally fine, you should work with whatever origin you're most comfortable with. And then if you discover that that sentence does not describe what you would most naturally give as the reference, then just adjust. It's not hard, right? So you know that the difference between here and here is 2.5 meters. So this is 1.7, and this is 0.8. You can easily juggle back and forth between the two. It's no big deal as long as you are paying attention. Are there any questions on this example? Okay, and this becomes doubly important when we start to have more than one dimension. So you can also use this strategy. Let's say you had an object M1, M2, M3, M4, and they're distributed not just in 1, but 2 dimensions. Well, you pick an origin for this. I guess let me move my M4 slightly. Pick an origin. Realize that that's your personal choice. I'd probably pick one that's on top of one of the masses, but you don't have to. And then what you do is you identify the x-coordinates, x1, x2, x3, x4. You weigh those to find xcom. So xcom is the sum of these guys. You do a weighted average of the x-coordinates. Weight them by how much mass is at each location, and you'll get the x-coordinate of the center of mass. And then follow the same exact prescription for the y-axis. Identify the y-coordinates, y1, y2, y3, y4, and get ycom. It's the weighted average of the y-coordinates. So in this fashion, you can actually produce an xy coordinate for the center of mass. Just speculating, maybe it's somewhere around here-ish or something. X, y. But again, the output of the equations will come out relative to the origin you've picked. So be aware of that. Your x and y coordinates are good for your axes that you're using. Okay, so that's how you find center of mass quantitatively in both 1 and 2 dimensions. And for our purposes, if I ask you to do that, you can either do it with a collection of point particles, which have easily identifiable coordinates, or thrown in there, like I did on the last example, there may be some extended objects which are relatively uniform, in which case you can just take those as being point particles at their geometric centers. So that's the basic gist of center of mass. Are there any questions on that? Yeah?
For the y column, M1, Y1, and then M2.
Oh, yes. I don't know what I was thinking. Yeah, so you're going to multiply each coordinate of each mass by the mass that's there. Any other questions? Well, it's an xy coordinate, so the sum of them wouldn't have any meaning, right? Because they're independent things. If you wanted to find the distance from the origin, I guess you could use Pythagorean theorem, but that usually a coordinate is okay. So the coordinate is what pops out most naturally. On the homework, you may need to do, again, just a little minor adaptation to make sure that it's expressed in the way that they want. Okay, any other questions before I move forward? Okay, so that's what center of mass is conceptually. That's how you calculate it. Now we're ready to move on to the second thing, which is, of course, the rotation part. So what about the rest of the object? If we can find the center of mass, that's the point that we know how it moves. What about the rest of it? There's some rotation involved. Let me give you a little bit of a preview where we're going with this. So we're going to embark here on a major unit, angular motion. All right. So let me give you an overview of where we're going with this. We're going to find that in many ways what we're just about to do is all the bizarro versions of everything that we've already discussed. So to give you an idea, the old stuff that we talked about before is called linear motion, also known as translational motion. Those are interchangeable words. We, of course, never called it that because we had nothing to confuse it with, but all the physics you know so far is linear or translational motion. It's how the center of mass translates or progresses through space. That's in contrast with angular or rotational motion. Again, same thing, just two different words for it. So we're going to be redeveloping many of our ideas, but rotationally. So first of all, we had the very first thing we did in the linear world was kinematics. We learned about displacement, velocity, acceleration, things like that. That was motion. First, it was just along a straight line, and then we, of course, learned that with components, we can think of more complicated motions as just composites of that, right? So a two-dimensional problem can be broken up into two one-dimensional problems. That's the beauty of components. All right, well, now we're going to do them all again. So displacement, velocity, acceleration, we'll have angular displacement, velocity, and acceleration. So angular displacement, angular velocity, and angular acceleration. So I'll go back through these one by one. You don't need to necessarily jot them down at this point. Just kind of get the big picture. And of course, our friends were the constant acceleration equations, right? So for that particular type of motion, where velocity changed smoothly. We have a whole toolkit which is ready to just jump in, our 5 equations. Well, there's going to be constant angular acceleration equations. There's so much similarity in this stuff that we're going to zoom through in a couple homeworks what it took us the entire course this far to do. Okay? There's only a few little things here and there where you have to watch out. Otherwise, it's the same ideas. Okay? So that was our kinematics. We learned to be expert describers of motion, just describing what's going on. We can speak about speeding up, slowing down, things like that in a suitable way. Then, of course, the next layer of the onion was why, right? Why do some things accelerate and other things don't? So that was where Newton's laws came in, right? We learned that there's an idea of inertia, that things like to keep doing what they're already doing. The reason why things accelerate or change their motion is because they're forced to. So we had things like, talked about force, and brought in, I guess, mass. Mass is a measure of inherent stubbornness to change. And of course, these are combined into good old Newton's second law, F net equals ma. And that was a nice tie-in, of course, because we can find the acceleration ourselves and then, of course, relate it to other parts of the motion. So go back to kinematics, right? Well, there's a rotational analog to force. It's called torque. You may have heard of a torque wrench, right? Or maybe the torque on a car, right? It's like the force, but such as to make something go in a circle instead of just in a straight line. So the rotational version of force is torque. There's even a rotational version of mass. It's called rotational inertia. So instead of mass being a measure of inertia, we have now rotational inertia. How stubborn is something to rotational change? You may ask, is there a rotational version of Newton's second law? Yes, there is. The net torque that you apply on something will angularly accelerate it. That's where angular acceleration comes from. And you can, of course, tie these in together. All right? So the next major unit after the forces method, what do we do next? What was the next major way of solving problems? Now I think we're in homework, halfway through homework 6. What do we start talking about? Work and then energy, right? So the work method, and then we kind of finally morphed it into the energy method. So we had such a thing as kinetic energy. We didn't call it this at the time, but it's actually translational kinetic energy. It's the energy of motion that something has by flying through space, having some velocity. Well, if you have an extended object, it's also possible that it just rotates in place. That's also energy due to motion, so there'll be something called rotational kinetic energy. So that's another new form of energy we'll have to incorporate. And then once we finished the energy unit, what was the next way to solve problems that we looked at? Momentum. So we're quickly approaching where we are now. We had momentum. We just called it momentum at the time. We will refer to it as linear momentum. Why not translational momentum? I have no idea, but people say linear momentum. Okay. And there is a counterpart. It's called angular momentum. I don't know why it's not called rotational momentum. No one calls it that, but I don't know why sometimes they use the translational and rotational, and sometimes they use the linear versus angular, because they're the same thing. Okay. And then we talked last lecture a little bit about momentum and energy together. And then what was the next topic after that? That was this. I just started that today, center of mass. Okay. I consider center of mass as kind of being the bridge topic between the two worlds. Because the center of mass ends up being the ambassador for the old physics, the linear or translational motion, but it also ends up oftentimes being the center of the rotation for the rest of the object. Okay? So that's where we're going. Let me give you a little bit of a roadmap. This stuff was homeworks numbers 1 through 3. That's in the can. Force and mass and all that stuff, this was homework number 4 through 6. Energy, translational energy, kinetic energy was the back end of homework 6 through, well, we'll use it for a while, okay, but it was heavily featured on homeworks 6 and 7. And I, of course, put it in with momentum, which is homework 8. Sometimes you have to worry about the energy in a collision as well. This one is definitely homework number 8, which I'll post for you shortly. Center of mass is homework 8 as well.